Distinguished colleagues, good afternoon, dear guests. It's April 20th, year 2022, 2 p.m. Moscow time, and we're beginning the panel session for the defense of the thesis by Natalia Masalaeva. The thesis is submitted for the academic degree of candidate of sciences in physics and mathematics. The specialization is 136 Optics. The topic of the thesis is non-classical states of light and atoms, preparation and application of quantum computing and simulations. Under the order issued by the Academic Secretary of St. Petersburg State University as of February 9th, 2022, number 911/1, I, Tatiana Golubeva, Doctor of Sciences in Physics and Mathematics, Associate Professor, Professor of the Department of General Physics 1 of St. Petersburg State University, was appointed the chairwoman of the board. The order also approved the members of the board, namely Igor Moshuk, Doctor of Sciences in Physics and Mathematics, Associate Professor, Professor of the Department of General Physics 1, Nikolai Bezuglov, Doctor of Sciences in Physics and Mathematics, Senior Researcher, Professor of the Department of General Physics 1 of St. Petersburg State University, Dmitry Kupriyanov, Doctor of Sciences in Physics and Mathematics, Leading Researcher of the Faculty of Physics at the Lomonosov Moscow State University. And today we have Maria Chekhova, our member of the board, who joined us remotely. Maria is Doctor of Sciences in Physics and Mathematics, Professor at the Max Planck Institute for the Science of Light in Germany. Maria, do you see and hear us? Yes, I both see and hear. Okay, thank you. Our candidate for the degree also joins us remotely today. That's Natalia Masalaeva. Natalia, do you see and hear us? Yes, everything is okay, thank you. As Natalia joins us remotely today, first of all, we need to decide and discuss it, whether we can continue our board session, considering that Natalia is working remotely. Igor, what's your opinion? Can we do that? Sure. Yes, sure. Yes, no problem. Maria, can we continue like that? Yes, sure. Okay, I also believe that we can continue our board session. Therefore, let us proceed. The decision is taken unanimously. And also we have a thesis supervisor, Ivan Sokolov, Doctor of Sciences in Physics and Mathematics, Senior Researcher, Professor of the Department of General Physics 1 of St. Petersburg State University. Okay. I wanted to warn you, as we have the broadcast of the board session, if we need some technical break, and if someone needs to leave for some minutes, warn us, because in this case I will announce the technical break, because during the board session all the participants should be on screen all the time. Okay, thank you. And I also wanted to say that the broadcast is on the website, and we may get some questions during the broadcast, and if these questions are submitted, I will read them out during the discussion, so all our listeners can ask questions, and you have an email address given on the page with live broadcast of the board session. And under the order on the procedure of granting academic degrees at St. Petersburg State University, approved by a local regulatory acts, the session of the board is valid, providing 2/3 of the appointed board members are present, and the total number is not to be fewer than 4 people. Our board consists of 5 people. Everyone is here today, so we have the quorum. And I kindly ask the member of the Department of Dissertation Board Support, Natalia, to fill out the attendance list. So, as for our agenda for today, it is as follows. First comes the chairman's brief presentation about the documents submitted by the candidate for the degree and their conformity with the requirements. After that, we'll give 20 minutes to our applicant for the degree for the presentation. After that, we'll ask questions on the presentation, only on the presentation. So answers by our applicant will follow. After that, reports on the thesis. The board members will deliver their reports, and the candidate for the degree will comment on these reports. And let's make it this way. First of all, one of the members of the board, his or her questions, and after that, the applicant provides answers at once after the report. So, what do you think about it? Okay. Everyone supported that. After that, we may have an open discussion, speeches of those present at the defense. Those who are not the members of the board may say something about the applicant, ask questions, and so on. And at that, I kindly ask you to introduce yourself, full name, academic rank, position. When I give you the floor, don't forget to mention that all. And after that, we will give the floor to the thesis supervisor. Then we may have a 5-minute discussion of the results of the broadcast, of the results of the defense, then open balloting. Afterwards, we're going to make a decision and the candidate's closing remarks. So that's our agenda for today. Any objections about it? So that's the agenda that we have at St. Petersburg State University. Well, if there are no objections, let us proceed. So, a thesis by Natalia Masalaeva for the academic degree of Candidate of Sciences in Physics and Mathematics. The specialization 136 Optics is titled Non-Classical States of Light and Cold Atom Ensembles, Preparation and Application for Quantum Computing and Simulations. The thesis was approved for the defense by the order of the Academic Secretary of St. Petersburg State University as of January 18, 2022, number 201/1. Natalia Masalaeva has prepared her thesis at St. Petersburg State University as a PhD student, and Ivan Sokolov is her thesis supervisor, and I have already introduced him. 4 published works describe the research findings, and all these articles are published in journals indexed in Web of Science and Scopus. So, pretty good, high-ranking works. And all the documents submitted by the candidate for the degree, as far as I'm informed, are found in the certification file of the applicant, and curator of the defense, the member of the Department of Dissertation Board Support, has all the copies of these documents. So we have all the documents, and there is a question whether we need to consider the whole list of documents submitted by Natalia. So that's the question to the members of the board. So are we going to do that? Or there's no need for that? No need. Okay, then we can shift to the content. Natalia, please, you have the floor. Yes, thank you so much. Dear members of the board, dear guests, my name is Natalia Masalaeva, and today I want to present my thesis for the degree of Candidate of Sciences in Physics and Mathematics. titled Non-Classical States of Light and Atoms, Preparation and Application for Quantum Computing and Simulations. The work was headed by Sokolov Ivan Vadimovich at the General Physics Department 1 of St. Petersburg State University. We've chosen the non-classical states of light and matter as an object for study for several reasons. For example, entangled states between light and matter are actively used in quantum communication problems, and they are also the basis of the work of quantum repeater. And above all, correlated states of light and matter can simulate multi-system systems like electrons in mesh. A non-Gaussian state of light is a promising system for quantum calculations and correction of mistakes. Therefore, we decided to make a goal to develop theoretical description of non-classical light and cold atom ensemble states, and to analyze their use for quantum calculations and simulations. As the work itself consists of literature review and 3 chapters, I would like to pay attention to the literature review because it has approaches and principles to be used in other chapters. First and foremost, I would like to dwell upon the process of atomic self-organization in the optic cavity. This process is the basis of all the results of chapter 3. Let us consider the system that consists of from N atoms placed in the Fabry parallel resonator that are illuminated in transverse plane by laser radiation, as demonstrated in the left. The pumping and the mode are built far away from the frequency of atomic transition, and as a result of interaction, the atoms start to re-emit photons in the field of resonator mode. And when atoms are placed evenly along the axis of the resonators, then 2 atoms located on the distances at half the wave of the mode of resonators emit make emission in the opposite phases, and that leads to destructive interference. And for some values that exceed threshold, under fluctuations, atoms self-organize into a periodical structure that can be implemented by 2 ways, as demonstrated on the slide. These both configurations provide similar amplitude of inter-resonator field, but with opposite phases, 0 LP, thus spontaneously destroying the discrete symmetry of Hamiltonian of the system. Another peculiarity of the use of resonator is long-range interaction between the atoms using the field of resonator mode. As the dynamics depends from atomic behavior in a local state of atomic distribution influences the inter-resonator field, and the change of it is felt simultaneously by all atoms regardless of the distance and initial atomic perturbations, and that leads to interactions between atomic densities. For 2-tier atoms, the photon can be absorbed by another atom, J, that leads to interaction of type spin-spin. The radius is limited, and in general case, by the resonator mirrors, and the distances do not depend on the distances, and the interactions do not depend on the distances between the atoms. And this can lead to ultra-hot states. In chapter 4 of the thesis, we dwell upon the scheme on the preparation of non-Gaussian states, including the Schrödinger cat state. Under this state, in quantum optics, we see as a superposition of 2 coherent states with opposite phases, as demonstrated here on the slide. And N is a normalization multiplier, and theta is an arbitrary phase multiplier. So you see the Wigner function to the right, and you see the projection on the phase plane. Currently, this state is interesting not just from the fundamental point of view, and it also plays an important role in quantum calculations. Such states are stable regarding the mistakes of certain type, and this was experimentally as shown when we used the CAD states for logical 0 and 1. Thus, the issue of preparation is relevant, and some ways of preparation are listed here on the slide, and the schemes considered in the last part of the thesis is dwelling with the last point, the use of non-Gaussian state. Now let us shift to the results obtained in the work. First of all, let's dwell upon the generation of compressed and entangled states in resonator configuration. Our model is given on the slide, and it consists of the atomic ensemble placed in the ring optic cavity. Atomic ensemble consists of cold random atoms with lambda configuration of the energy levels. And we presume that at the initial point of time, all atoms are prepared in general G state using optic pumping, and the field of cavity mode is in vacuum state, and connection mirror has the classical control field that interacts with atomic cell at transition GF, and that we believe that control field is built far away from the atomic shift, and due to this interaction the atoms undergo Raman transition from G to S and emit Stokes photons at frequency omega c that is supported by one of the longitudinal modes of the resonator. And we got Heisenberg equation system, and it was reduced for boson slowly changing operators of the field of cavity mode E, and for S atomic coherence that is collective. And K here is a non-dimensional parameter of connection that depends on the Rabi frequency. And this system can be rewritten as Bogoliubov transformation that generally may look like shown on the slide. The theorem on the reduction says that matrices A and B included into Bogoliubov transformation can be represented by three matrices, and U and V unique matrices of turn, and A and B compression matrices. And we found boson amplitudes of eigenmodes that undergo compression, and expressed field flowing from the resonator that has a set temporal profile given on the slide, and the operator of spin coherence in the end of the generation process. And in order to assess the entanglement stage between generated field and atomic ensemble, we use the Doan criterion that allows to assess the presence of correlations between quadrature operators, and a full exclusion of the field from resonator. Doan criterion looks like that, shown on the slide, and R is the coefficient of compression of the eigenmodes of the transformation of Bogoliubov, defined by diagonal elements of the matrix. And above all, we found the temporal profile for the parameter of connection that supports the flowing of the field from the resonator with a set profile and unlimited length, tau log. That is 15. And from the graph, we see that in order to achieve more entanglement, we need to have a more intensive field. The yellow point, where the connection parameter is 0 and it changes sign, responds to the change of regime from generation of pairs of quants to addition of pairs into pumping quantum. And this behavior is associated with the fact that the resonator wants to exponentially expand this front of the signal. Similar effect can be observed in the process of reading of the quantum system from the memory of the resonator configuration that leads to the deterioration of the efficiency of the entire protocol. However, in our case, even for short signals regarding the lifetime of field in the cavity, we can achieve the compression level and entanglement of the output signal and atomic coherence, and this is reflected in the first item for the defense. However, the application of very intensive control fields has a lot of harmful nonlinear effects like four-wave mixture, light shifts, and so on. Therefore, we wanted to choose a cavity that could be used to extract a signal with a set form and length using a less intensive control field. Here on the slide, you see three images that respond to different entanglement degrees and mean photon number of the in the generated impulse. And here you see all the differences in light, and the length of the impulse is fixed. T is constant, and we see the change of the lifetime for the field of TC. The first curve, and tau log equals 1, so it is depicted in blue, is responsive to a significantly non-adiabatic regime. And the last curve, yellow curve, demonstrates the so-called bed cavity approximation, because the life of field in the cavity is much smaller than the length of the impulse. And as shown on the graph, starting from bed cavity and increasing the life of field, the entanglement and compression level can be achieved using less intensive control field. And all the above mentioned allows us to give the second provision for the defense. In the next chapter of the thesis, we study the issue how system that looks similarly can be used for the simulation of processes for hard body physics. And in this case, we're going to consider the Bose-Einstein condensate in Fabry-Perot cavity. And we will believe that atoms, three-level atoms with lambda configuration of energy levels. In this case, we're going to consider atomic self-organization as described in all the literature review. But in this case, the condensate is eliminated by not one but two control fields in the transverse plane with omega-1 and omega-2. And this configuration allows us to get long-range interaction of induced mode of resonator between atomic density spins and combined interaction between spin and density. And here, the field of resonator mode quickly reaches its stationary value that can be used for effective spin Hamiltonian acquisition that contains only atomic levels of freedom. An obtained Hamiltonian includes anisotropy, TJVW spin model, and long-range interaction between X and Z spin components. And in turn, the spin model includes the Heisenberg long-range model, XXZ, with effective homogeneous magnetic field with long-range interaction between atomic densities, that second line, and interaction of atomic density with different spin components accordingly. And connection coefficients included into Hamiltonian, represented here below, have similar dependency on the position of spins, and the amplitude of coefficients of binding depends on the Rabi frequencies of the control lasers. Thus, the interaction transformed the Bose-Einstein condensate into the combination of interacting spins described by Hamiltonian. And this Hamiltonian, depending on the parameters of connection and system, implements different spin models with connection coefficients that can be mastered using the Rabi frequencies of control lasers, and this gives us a third provision for the defense. Within the framework of approximation of the mean field, we obtained the following phase diagram that shows the dependency of field amplitude in the resonator from Rabi frequencies of mastering lasers, of control lasers. And this diagram includes 4 different fields. So you see them demonstrated on the slide, and they are different with different magnetic orders of the spin components. Thus, in the field where mean number of photons in the resonator mode equals 0, the system is in ferromagnetic state, in spin state, and the direction of spin components is defined by effective magnetic field, as demonstrated on the slide. For non-zero value of the amplitude in the interresonator field, let us consider the behavior of spin components for this blue dot. As omega-1 is more than omega-2, the behavior of the spin is defined by the coefficient of connection and magnetic field. And this is demonstrated in the modulation of the Z component of the spin. The major impact on X is done by effective magnetic field that directs it into negative direction in order to minimize the interaction energy. Such analysis was conducted for all the 4 phases, and it allowed us to make the following conclusion. Long-range interaction between atoms caused by the connection with the field of resonator mode allows us to get a broad spectrum of interaction between atomic densities, pseudospins, and combined interaction between atomic densities and pseudospins. And last chapter of this thesis is dedicated to the preparation of states of Schrödinger cat using non-Gaussian resource state. And this scheme allows us not just to create a Schrödinger cat state, but also general states that are superpositions of two copies on the input. And the scheme to prepare Schrödinger cat state using a non-Gaussian resource state was offered here. You see this link in the bottom of the slide. And the input, we have two oscillators. The control oscillator is in arbitrary position, and the vector can be described like that. And auxiliary oscillator is a non-Gaussian state, and that's the cubic phase, and you see it on the slide as well. And to oscillators, we use a unitary transformation, CZ, and then we measure the impulse. And we believe that the result of this measurement is YM, and when the wave function of the oscillator looks like that, and is a normalization multiplier. Thus, as a result, the wave function of the oscillator goes to the output, multiplied by additional factor phi that can be represented as IRI function. And we can use stationary phase method to calculate the integral and get the following expression for the wave function in the output that demonstrates that the wave function on the output is a superposition of two contributions. So that's the graphic presentation of the evolution of quadrature amplitudes. On the next slide, you see the graphs for fidelity between accurate decision and decision got using stationary phase, depending on the result of measurement and parameters of cubic phase. In this case, in color, we demonstrate the difference of value from 1, and you see the combination of wave functions. Three graphs, A, B, and C, correspond to different initial states of the control oscillators. A is vacuum, B is Fock state with the number of photons that equal 1, and C with 2, where the number of photons equals 2. And we see some bad correlations, and such areas can be divided by vertical lines as demonstrated on the slide. And these lines define the area where we may be unable to find the intersection between the results of change of impulse of the auxiliary oscillator and parabola. Thus, this method may not work in some areas to the left. Now we can assess how this scheme allows us to prepare the Schrödinger cat state. Believing that oscillator is in the state of Fock, a wave function on the output can be represented like shown on the slide, and theta is the phase between two terms of superposition on the output, and squared root from gamma m divided by 3 gamma defines the shift of copies along the axis of the impulse. Then for vacuum state on the input, the wave function can be described the following way in the coordinate representation on the basis of coherent states, where you can see at once that we have the Schrödinger cat state on the output with an amplitude of coherent state depending on the result of the measurement of the impulse of auxiliary oscillator and a cubic phase parameter. And below on the slide you see the image for differentiating fidelity from 1, and it is calculated using Airy function and wave function given on the slide in the upper part. And to the right you see the functions of Wigner for accurate wave function on the output for marker points. These points lie in the area where fidelity with cat state is good, bad, and moderate. And if gamma is more than 1, and that's the dotted line here on the slide, then the deformity will not significantly provide a significant impact, and that's this area of fidelity that is close to 1. Similar results can be obtained for Fock states with 1 or 2 photons in the input. In this case, the considered protocol allows us to get the so-called shifted Fock states. And on this slide, the first line corresponds to the input states with 1 photon and the second one with 2. And once again, we provide graphs for fidelity in Wigner function. And in order to assess the deformities, we are based on the same ideas, and in the rise of photon number in the input state, the area where fidelity is strongly different from 1 is growing. And this can be explained by the fact that Taylor expansion works worse here. Thus, this work allows us to make this last provision for the defense. The scheme with the use of non-Gaussian resource state and operations of entanglement allow us to get the Schrödinger cat states and general states that are superposition of two copies of state on the input symmetrically distributed in the phase space of the impulse axis. And here you see the testing, the articles, and the provisions for the defense. Thank you. Thank you, Natalia, for the fascinating report. Questions to Natalia? Any questions? So use the microphone, please. Yes, Maria, thank you so much. So in any order. Yeah, I'm ready to ask 2 questions. Well, right now, the questions on the report. Yes, sure. So you talked about non-Gaussian states, how good they are, and I really like them as well. But you said that they are good because they help. They are not sensitive to mistakes in some protocols. But here's a question. They are pretty sensitive to losses, to my mind, especially such Schrödinger cats, with these full-fledged cat states. Can you please comment on that? Yes, sure. Well, still, in the article, and I provided the link on the slide, it was demonstrated that these mistakes associated with a photon loss can be controlled, measuring the even state. So as basis states, we used 4 cat states with different phases, and after 4 losses of photons, the state shifted to the initial basis state. But measuring this evenness at every point of time, with some periodicity, we got it that if even state changed, it means that we lost 1 photon. And if we lost it twice, and evenness got back to the state. So, yeah, this may happen. My second question is as follows. On slide 13, that's about non-Gaussian states as well. I did not get it completely. This parabola, what does it depict? And what kind of blue line is that? Is it Wigner function or not? That is the representation of 2 oscillators, the control and auxiliary, one on the plane of impulse coordinates. That's on the phase plane. And in blue, this blue circle is the Wigner function to one state in vacuum. Is it a vacuum state or what? Yeah, it may be the vacuum state as well. And in this case, the parabola is not the Wigner function. We don't have such Wigner functions, yes? The blue circle is the density of distribution of our impulse and the coordinates of the control oscillator. And as we are not initially talking about the state of the control oscillator, so it is some state. And as for the parabola, that corresponds to auxiliary oscillator, that is in the state of cubic phase. And why can we show it like that? Because the Hamiltonian that should influence the compressed vacuum and the compressed state along the impulse axis, this Hamiltonian is a cubic in coordinate. And if we write Heisenberg equation, we'll have it that impulse at some point of time depends in a quadratic manner from the coordinate. So that is the quadratic dependence. So that's not the state, but rather an evolution that you show. Oh, I got it wrong. Yes, evolution at for a single period of time, so to say. So initial points, if I take some state, it means that all points will move along this parabola and to one direction if it is an evolution. We need a direction. We do not consider time evolution. That is just a demonstration image that allows us to logically show that in this system we have the following situation. Well, unfortunately, I didn't have time to describe it better. Yeah. Okay, thank you. Maria, are you satisfied with the answer? Yeah. Yes, to some extent. Natalia, I have a question as well on Schrödinger cats. And the most interesting aspect of your work to me. You said that as a control oscillator, you can take different states. And you demonstrated 3 options. A vacuum state, a 1-photon state of fog, and 2-photon fog state. And I believe you thought what's better for quantum calculations, because quantum calculations are given in the title. So my question is associated with that. What's better for quantum computing? What state is best here? Well, right now, the works that I've seen, yes, thank you very much for the interesting question, first of all. Those works that I've seen, they use the cat state as logical zeros and ones, and the shifted states of fog that we can also obtain. Right now, I haven't seen many works dedicated to the issue whether they're good for quantum computing, but in our scheme, it's hard to not to get an overlap. So you can get good cat states, but increasing the number of photons at the initial stage of the control oscillator, these states are not that good for quantum computing. Okay, thank you. Other questions on the presentation? None? Okay, in this case, we can shift to the reviews. Nikolai, you have the floor. Well, I will not dwell upon the relevance of the topic because every word in the title demonstrates it. These are fields for quantum optics and informatics. Therefore, I switch to the essence. And I'd like to say that the thesis looks pretty well. It has a lot of illustrations. It has a lot of literature sources. And at once I wanted to say that the majority of results obtained are obtained analytically. And in fact, the represented computing is an illustration. As for the material, it is distributed across the 4 chapters and 6 appendixes. And appendixes have all the mathematical details in order not to complicate the text of the thesis with these technicalities. The first chapter is an introduction chapter, and it contains a pretty good review of 20 pages of adjacent topics on quantum optics, on quantum informatics, and we have an emphasis on the specificity of set problems and applied methods. And chapters 2 and 3 are aimed at the study of Raman, scattering of light on ensembles of cold atoms that are placed in the cavity with one mode. And the level system is chosen. And you see 2 components of the state. The Raman scattering of light is executed with a control laser, and with quantums in the lambda scheme. In the second part of lambda scheme, we see the resonator mode. So the configuration, atomic configuration, is chosen so that in Raman scattering, the energy would distribute into two quantums. One quantum in the resonator mode, and the second quantum is in the collective spin of atoms. And as a result, you get the entanglement between light and matter, and accordingly, the flowing light through a semi-transparent mirror is in compressed state. So an important result of this chapter is the connection between the degree of entanglement, degree of compression, and the number of photons captured by the resonator mode. And the next important point that the thesis raises is the following one. How can we organize this spatial profile of the control light in order to get a convenient temporal profile of the flowing light? And that's a typical non-reverse problem. The solution for non-reverse problems are incorrect, but in this case everything looks great. And in order to establish the connection between input and output temporal profiles, we use the author used a good method of impedance correlation. And in the analytical form, and the author managed, and by the way, the author has a lot of analytical results. All the chapters have pretty good formulas. So the author manages to get the integral connection between input and output profiles, as I've started to say. And yet another important point is that all the consideration is conducted beyond the framework of characteristic bed cavity approximation. So no restrictions on the good value of resonators, and this increases the sphere of practical application of the results. In Chapter 3, we see the complication of this model of interaction between light and matter. The atoms shift to condensate of Einstein base, and we have an additional control laser that works in pair with the resonator mode. And at that, we see the study of Raman scattering process, and this allows us to use adiabatic elimination of variables associated with the excitation state. As a result, we get Heisenberg equation, and the Hamiltonian describes the evolution of components of major state of the condensate. And we see the interpretation of components of the major state as spin components. Thus, our condensate has magnetic characteristics, and accordingly, the effective Hamiltonian describes all kinds of interactions that happen between the moments of the condensate. And every term is expanded into a sum of different terms, and every term is explained by certain processes of scattering of light on the matter. And we have terms that are associated with elastic scattering. And also at that we have different shifts, and in Hamiltonian we have the potential of optic meshes. So these are local interactions. And also we have Raman scattering of quants of the control fields, one over another. And in this case, it leads to the fact that we see the change in the spin direction. That's also local interaction. And formally in Hamiltonian, we have an efficient magnetic field that is local as well. And finally, the most interesting interaction is associated with Riemann scattering of quanta of the control fields into cavity mode quanta. Yes, I continue. So this leads to long-range interaction, as it was demonstrated that as a result we may have very interesting, depending on parameters, and there are a lot of parameters, and varying these parameters, the frequencies of Rabi, of control fields, or two-photon structures between the components of major state. We can vary, in these terms, we can there are 6 terms in the effective Hamiltonian. We can some terms strengthen and others, and thus we can modulate all the processes of interaction of spin magnetic moments in oscillation. So we can model interaction density, spin-spin interaction, and we can model a combined interaction density to spin. And what's also important is that when we exceed the Rabi frequency, we can have a self-organization and different magnetic phases. And it was demonstrated that we have 4 such types of magnetic states of the condensate. And what's important is that these states can be shifted from one to another using the change of the parameters of our system. And then the last chapter is associated with the studies of generation of the new method of Schrödinger cat states. These are fascinating states with a lot of possible applications, and here we see the use of key point, non-Gaussian resource. So we take 2 oscillators, one is Q1, another one is auxiliary 1. The auxiliary oscillator is in the so-called cubic state, and the major oscillator, its wave function is corresponding to some final distribution of densities in the coordinate space. And then we use entanglement or CZ operation, and then we measure the impulse value of auxiliary oscillator. And after that, the wave function of the main oscillator, in ideal case, it is in superposition of 2 copies of initial states. In coherent superposition, I'd like to emphasize that. And what's important is that everything is done analytically. Therefore, we managed to describe a good fidelity criterion, and choosing the optimal parameters, it allows us to create cat states of good quality, so generate this good quality cat states. And that's a classical method that provides interpretation of how it happens on the classical language. She takes exact states for the main oscillator, not for the auxiliary one. And then using Hamiltonian equations, on the classical language, the author considers the evolution of all the states as a result of protocol actions, and everything is quite obvious. We see how these cat states emerge. We see how this method can be used in more complex systems. And once again, I would like to repeat that the thesis is pretty good. Certainly it has certain drawbacks, like inaccurate quotations, some misprints in formulas, and in the major text I won't just give them all because they are not important at all, and they do not compromise the high quality of the thesis at all. The credibility of results is obvious. It is demonstrated by publications in 4 high-ranking journals and testing at more than 10 conferences. Therefore, it's not surprising that the thesis gives us a very good impression. The author got a lot of fascinating results, and certainly it meets all the requirements. of St. Petersburg State University, and I believe that Natalia Masalaeva deserves the academic degree of Candidate of Sciences in Physics and Mathematics in specialization 136 Optics. And finally, I have two questions that I wanted to ask. The first question is dealing with Chapter 3, and it sounds like that. In Section 2.6, we're discussing the method of coordination of impedance. On page 53, in line 2, you say that amplitude of collective spin is purely false, though when finding parameter of a connection, the initial value of this amplitude is taken as a matter value. That equals 1. Is it expedient to judge like that? And two other questions are dealing with Chapter 3. Second question. The description of Heisenberg equations do not contain this wording of spatial border conditions for spin condensates. Should they be spatially periodical? And if yes, then what is the period? And the last question. The method of continuous approximations provides for iteration continuity of solutions. And in one stationary or non-stationary variant, did you decide the spin equations? Thank you so much. You described the work of Natalia once again, so we understood it better. So, Natalia, you can answer. Yes, thank you so much. The first question is strongly associated with the question of Tatiana Yurievna, and I wanted to answer it as well. So I wanted to mention that coherence phase of the ensemble influences the phase of connection parameters. So we see it that if we take the coherence is purely false, then the parameter of connection associated with Rabi frequency is a matter. And if the coherence is a matter one, then the connection parameter is false. And similarly to parametric scattering, this choice influences what quadrature will be compressed and which will be expanded. Therefore, this provision does not change the physical value of the problem. And as Nikolai mentioned, we chose it at one point when it's false, and another point it's matter-like. So that was done to construct the connection parameter. Okay, thank you. So I'm satisfied with the answer. Okay, thank you. As for the second question on periodicity of spin condensate field, yes, really, spin condensate fields are periodic because the Hamiltonian of the system itself, and here you see the emerging optic potential, so they are periodic ones. And the period is the wavelength of the field of resonator mode, and we depict this spin components on one wavelength. So as I see it, you have this margin conditions replaced by periodicity conditions. Yes. And the last question on how we resolve the system of equations for amplitude for the interresonator field, intercavity field, and spin components, atomic ensemble components. In this case, we resolved everything in a stationary option. First, we found the stationary state for the resonator mode, and then we placed it into next equation and found the general state of condensate. Yeah, may I provide a proposal here? As you write effective Hamiltonian, maybe it's better to find the general state of the condensate. Maybe it's easier to use Hartree fork method that allows you to do that more accurately and quickly to obtain the final result. Probably, I can't say it for sure. Yeah, I can't say it straight away. Okay, thank you. Yes, thank you so much for the comment. Okay, Nikolai, are you satisfied with the answer? Sure. So, dear colleagues, we continue, and I really ask you to stick to the time limit because all the reviews were already published on the website of the university. Therefore, we mentioned just the key points. Dmitry, please, you have the floor. Yeah, got it. I'll try to be very brief. Therefore, Natalia, I beg your pardon if I'll be too brief. As for the general characteristic of work, this science, quantum optics, is focused on the study of correlations and some informatic applications. It is pretty old, or rather mature, so to say, and it's clear that the experimental base is now being developed, and now we can unite resonators with cold atoms, and this provides us a certain theoretic challenge. Therefore, this work is very important, and I wanted to mention that as well. And then, I wanted to unite the first chapter, so I'll omit the first chapter. It was already commented on. And as for the second chapter and the fourth chapter, I wanted to unite them because they have general goal of preparation of quantum states of light and their depiction in the atomic subsystem. And I will be a bit skeptical saying that this problem exists for a very long time and it would be nice to resolve it just straight away simply, but these quantum repeaters were offered in 1998. They are still undone, and the question of whether they will be done is still open. However, we need to move forward in this direction. And here you mentioned for chapter 4 whether we have a kind of win for this macroscopic quantum state. I don't really like the analogy with animals here because that's not what Schrödinger meant. But this macroscopic state, quantum states. So you have a qubit here, but it has a lot of photons, and we can speculate to correct some mistakes. So some theorists predict it. So chapters 2 and 4, I believe, support what's being done, but the prospects are a bit vague. And as for chapter 3, it was really interesting for me. It is associated with quantum computing directly and quantum simulation, as they call it accurately right now. That's a more suitable term. And strangely enough, the connection system is more simple and the progress there is not that impressive. And in quantum computers, in hard body platforms, we see it already. And what Natalia offered, and I see Helmut-Rich ideas here as well. So that's an interesting idea. That's what's on offer. You take a condensate, and that's a quantum state. But if we take interaction into account, it is a bit aggregated. And you can use a trap to place it into the resonator, and that's what's being done. And then if we start the excitation, it starts to interact with the resonator, and we see the formation of this mesh structure that is experimentally observed. And it is offered to use this optic interaction channel through the resonator as a quantum tie in collective interaction. And as a result, we get complex Hamiltonian spins, this kind of bridge. And it's Landau functionality that emerges though the author did not call it like that. However, the thing is that you, on resolving the problem, you can still model this system for spin hard body platforms. And following the advice of Tatiana Yurievna, Natalia, I beg your pardon, I can't say more positive words. I'll just read my criticisms. In Chapter 2, we can critically mention that quantum repeater problems have been in place for more than 20 years, and the physical schemes did not provide a practical result. Unification of cold atomic ensemble and resonator is hard to implement technically, and the introduction of atomic ensemble to the laser cavity provides for additional optic fields that negatively intervene the quantum interface. And it is also hard beyond the borders of magnetic traps to provide high optic density of the ensemble. Therefore, the author should think about it in the future. A second remark. I have some questions on Chapter 3. In Landau theory and in its summarizations, the time of phase transition near the critical point is continuously growing, and the application of considered model is restricted by the length of some spontaneous processes that shift atoms to other sublevels, and this is not discussed in the thesis. Maybe we have some contradiction here. The third remark. The author describes the existence of parameter of the order of the condensate that depends on the coordinate of phase transition. And we know that phase parameter gradient for the order means the movement of condensate from the whole microscopic object. And along with that, you see the extremum of functionality of Landau for stationary conditions. And fourth criticism, why do you lack temporary argument for Heisenberg operators? And this effective Hamiltonian does not look pretty assuring. And in Chapter 4, we can see that the offered protocol of preparation of hard superposition states of the oscillator is principally based on the introduction of Hamiltonian with a cubic nonlinearity. Any relevant physical scheme is not discussed for the Hamiltonian. And the key phrase is that all these criticisms do not compromise the overall high value of this work. Huge work, and I believe that Ms. Masalaeva deserves the academic degree of Candidate of Sciences in Physics and Mathematics in specialization 136 Optics. That's it. I hope I did not forget anything. Okay, Natalia, your answers. Yes, thank you so much. Thank you so much, Professor. And I'll start with the first criticism on the unification of cold atomic ensemble and the cavity. I wanted to note that surely you're right. For full theoretical description of such systems, we need to take into account the magnetic optic trap, as it was considered by authors in article that I provided a reference to on the screen. And I wanted to mention that indeed the experimental difficulties associated with the placement of atomic ensemble into the resonator easy to overcome, and right now we have impressive results for the implementation of hubs of quantum repeater. For example, on the slide you see the image of an experimental article from Nature Photonics, and experimentally they implemented the entanglement between three atomic ensembles placed into optic resonators. And at that, the role of the resonator in this system is very important, because without resonators, the efficiency of this entanglement would be negligible. The resonator allows to obtain some decent efficiency. So that's for the first comment. So is it okay? Dmitry? Yes, sure. Yeah, I beg your pardon because I can't hear without the microphone. As for the second remark, at the time of phase transition near the critical point, indeed, and I agree with you, everything is correct, but let me clarify this question a bit. Maybe I was not that understandable in the text of the thesis. On page 70, I describe a different thing. I describe the temperature of atoms in the stationary state. And for an open system, it is not zero. And in general case, the flow of field from the resonator mirror may lead to a non-heated state. And the relaxation speed of atoms to this state, as it was demonstrated in article referred to, is oppositely proportional to the value of our atomic cloud and speed of damping of the field in the cavity. And in contemporary experiments, this value, this gamma, is several seconds, and it allows us to say that atoms stay in the initial heat state. And as for the comments on the observation of systems near the critical point, yes, you're right, but we do not trace the process of self-organization that happens. Yes, to some extent. And as for the third remark, on the gradient of phase of the parameters, we work with the optic mesh. The group speed of condensate is defined by formula given on this slide. And we are in the minimum of dispersion correlation. Therefore, the group speed equals 0 in our case. Well, I believe you didn't have this formula in the thesis. No, that's just for your question. Well, your answer made me think more about the issue. As for the fourth remark, on the absence of time argument, I wanted to mention that as we are interested in normally ordered average values, we can omit Langevin noise operator, and at that, in these works given on the slide, instead of substantiation into the movement equation in order to then restore Hamiltonian, they used perturbations theory, and it was demonstrated that generally these methods are similar. Perturbations theory and direct substitution for such systems. Okay, but you should have been more accurate in the wording. Okay, yes. And as for the states with cubic phase, and Maria Vladimirovna also asked this question. So this question is really interesting, and very volumetric. I did not mention it in the thesis, though I should have done it. The implementation of this state is an interesting problem. Currently, it is demonstrated by the number of theoretical works that I found and read on the topic, and the experimental studies in this direction are still ongoing, and the schemes are quite polymerous, and they allow to generate the cubic phase state. And in article of 2020, it was demonstrated that you can use 0.1 state, but the efficiency issue is still there. And this scheme is very complex. It requires nonlinearity of third order environment, and also two compressions. And recently, another mode was offered to create the state of cubic phase using three compression state, three photon parametric scattering. But that is in microwave regime, but the studies are ongoing, as I've mentioned. Okay. Well, I'm satisfied, and I'm not sure whether Maria is. We'll ask about it later. So, Dmitry, so you're satisfied with these answers? Yeah? Okay, in this case, let's ask Maria about it. Maria, first of all, you have the floor to read your review, and after that, the questions, and please be very brief, as brief as possible. Thank you so much, Tatiana. I won't take too much time because everything was already mentioned on the thesis, and second is because I'm the only member of the board who is not a theoretician, but rather a practitioner. Therefore, your wonderful set of instruments is not quite clear to me. I wanted to say why I like the thesis. I really liked it. I believe that's a brilliant work. And as for the physics that the work considered, we have atoms, we have light, and in chapter 4 we also have pure photon states that are being considered, and above all these analogies like ferromagnetics and anti-ferromagnetics, and that's always fascinating. So this thesis is brilliant from the point of view of physics because it covers physics problems, and above all, I really liked the language of the work, and I really liked the presentation. So everything was brilliant. Therefore, I won't say more about the work, and I'll shift to criticisms directly. Yes, sure. It doesn't mean that my opinion is negative. It means that everything good was mentioned before. So my criticisms are as follows. Naturally, I always looked at the issue as a practitioner. I wanted to understand whether it's real to reproduce it in the experiment. Therefore, in chapter 2, it seemed to me that comparison with real opportunities is not sufficient. So I wanted to know the parameters. The parameters of the experiment and how real is that. And the most important thing is that if you have entanglement, Raman transition causes entanglement of atomic variables with photon variables. Surely, and we know that the presence of this entanglement leads to simultaneous compression, both for atomic variables and for photon variables as well. And I wanted to understand how to observe this compression for atomic variables. Maybe you know it, but I do not. So are we going to answer questions step by step, or should I read all the questions at once? Yes, you better read them at once. And then the final phrase, yes, sure. Yes. And as for other remarks, they are more in the form of writing. Some notions were described in details like fidelity, so the author described what fidelity is, though people in the field know that. And at the same time, I had to remember what ferromagnetism and anti-ferromagnetism are. So this TGVW spin model, I believe, it's not a well-known thing, so you should have described it in more details. And the last remark, this chapter 4 is practically not connected with other chapters. I believe we should think about it. And the fourth remark is on the form, the terms that he used in the work. I believe they are not all correct. For example, about the reminiscence and photon pumping size is, well, that's not an exchange here, but in this exchange you still have something left for stocks and for anti-stocks. And continuous and low photon regime comparison is not correct because we have continuous variables. And the use of continuous variables is possible even in application to single photon states. It doesn't mean that that's a multi-photon regime. And in the work there were contradictions of low photon continuous regimes. And then IRI or ERI functions, anti-component condensate. It's not that obvious that these are similar atoms within the framework of state spin up, spin down. I believe it's called condensate systems from different atoms when you unite condensates from different atoms. And these criticisms do not compromise my conclusion, and the conclusion is that the work by Natalia Masalaeva titled Non-Classical States of Light and Cold Atom Ensembles, Preparation and Application for Quantum Computing and Simulations meets all the requirements to these works, and Ms. Masalaeva deserves the academic degree of Candidate of Sciences in Physics and Mathematics, and that's it. Maria, thank you so much. Natalia? Yes, Maria, thank you so much for the valuable remarks. I agree with that all, especially as for the use of terms. We may have some confusion. And as for your first remark, this question was asked by Tatiana Yurievna, so let me shift. So how can we measure this entanglement? In order to measure the entanglement, initially we calculate spin excitations toward an atomic ensemble, and this can be done using the reading protocol for quantum memory. And the reference, and I'm one to the article, and I'm one of the co-authors here. So in this article, this process was considered. Therefore, generally, as for the reading, this mechanism is already developed. And how to measure it directly? How to measure this entanglement directly? So we offer, after the reading of spin excitation, we offer to send two light signals to the plate, and the quadrature of fields after the passage of the plate will coincide with the relative variables of the following waves. And for first channel, it will be the sum of quadratures of the coming fields. Therefore, it allows us to assess the Dern criteria using homogeneous, using this homodyne approach. And may I ask, this E, so those were variables of light and atoms. Now it's just light. Oh, okay. Okay, then it's clear. So I didn't know how to define it in order to combine with the Dern criterion. Okay, now it's clear. Thank you. And as for the second remark, as for this TJVW spin model, well, as far as I know, as other spin models, this model describes the behavior of electrons in crystallic mesh in particular. The link given here on the slide shows that this spin model can be useful to obtain high temperature superconductivity. And overall, that's it, what I can say about this spin model, unfortunately. And as for the third remark about the preparation of auxiliary Gaussian state. I hope you were satisfied with my previous answer. Yes, I really like to answer, especially the Wigner function with 3 angles. Yes, that's 3 photon. Yeah, I know. I know this work. Thank you. So, Maria, all your questions were answered. Maria, are you satisfied? Yes, sure, fully. Okay. Now we shift to the next speaker. We don't have one practitioner in the hall. We also have Professor Maszek, experimenter, optics expert. So please, you have the floor. Dear colleagues, I'm the last. No, Tatiana is the last. Okay. And it's hard to add anything to the analysis of work that colleagues provided. And I won't add a thing. I agree with a very high level of this thesis and the need for, and I agree with the practical importance, and that's a list of ideas and fields to be considered by future experimenters and current ones as well. And I want to mention that this work is done at a good level, and the applicant has demonstrated her qualification pretty well in this direction, and surely she's an established scientist. And remembering the wish of Tatiana to be brief, I don't have any significant criticisms. And in conclusion, I can say that the present work complies with the requirements established by the appropriate order, and Natalia Masalaeva deserves the academic degree of Candidate of Sciences in Physics and Mathematics and specialization Optics. And I wish Natalia further success in work. Thank you, Igor. And no need for answers? Yes, no need. I just praised her in my review. Okay, thank you. And I therefore close this part by my review, and I want to say that that's a brilliant work that delicately combines both applied aspects. For example, Chapter 2 provides answers to questions that are purely technological. What fields we need to use in order to get what could be used in practice later on. And at the same time, Natalia dwelled upon pretty fundamental aspects on the generation of new states that no one discussed or saw before. So these are the Schrödinger cat type states when you finally get non-trivial Schrödinger cat states with an oscillator that controls it in non-vacuum state. I believe that's a fascinating field for further study, and it would be nice to develop it later on. You have already answered part of my questions, therefore I will not read them. I'll just start with question 3, and it was as follows. In the end of section 2.6, you said that for the compressed states, it is possible to obtain the necessary level of compression using the capacity of the control field. But at that, it is obvious that there is an obvious restriction on the capacity of the control field, and it would be nice to have some estimates, because at large capacities we will obviously have certain side effects, and it was already mentioned in the work. Therefore, it's obvious that not everything can be done using just the capacity, and it would be nice to understand what is possible. Yet another comment. The ideas described in section 4.2 allows us to make a a conclusion that the lesser value of nonlinearity we use, the more is the distance between the copies of input states that we can get. And we need to get spread copies, so we get a paradox result, and this result, I believe, should be described in more details, because what you have here with marginal cases approximating 0, so it would be nice to mention this analysis in details. And it would be nice to get an explanation of the results presented on figure 4.3, where with a drop of nonlinearity you see the rise of the phase value. And once again, there is a question on the transition to marginally low coefficients of nonlinearity. That's the fourth question. And the fifth question is as follows. The method of preparation of non-Gaussian states described and offered in Chapter 4 is probable. Therefore, one of the key characteristics of the process is the probability of implementation of the measurement. And in the work you provide certain figures, but you don't give the assessment of probability, and it would be nice to have it described. What will happen with probabilities of values that you provided in the work? And these remarks do not, reduce my rapture about this work, and I believe that this work deserves all the support, and it meets all the requirements, and I believe that Natalia deserves the academic degree of candidate of sciences in physics and mathematics in specialization optics. Yes, thank you so much, Tatiana Yurievna. Thank you very much for your valuable remarks, and I'll try to answer. And as for your third remark, certainly you're right. Not everything can be achieved just eliminating the atoms with an excessively strong laser. And indeed, the assessment on squeezing, depending on the capacity of laser, would be expedient. But unfortunately, it was not given in the work. And as for restriction factors, I can know that as we work with the Raman approximation, and we're going to illuminate with a very powerful laser, we'll just go beyond the borders of this approximation. And if we use a powerful laser, once again we have different light shifts, and we may get an addition of a 4-wave mixture. So that's it, what I wanted to say to this remark. Okay, it's clear. And as I wish, it would be nice to get certain assessments in the work, just for future works. Yes, sure. No doubt about that. And as for your fourth remark, the marginal cases, indeed it's interesting that the smaller the coefficient of cubic nonlinearity, the better the spread of the copies of our cat state, and certainly that's what we wanted to achieve. But when we reduce the cubic connection coefficient, the deformities that emerge, as shown on the slide, they really reduce the quality of the cat state, and therefore this margin for us is not interesting and demonstrative, because that is not the cat state at all. Maybe we have some optimum here. Yes? It can be obtained from our condition that the product of measured impulse of auxiliary oscillator and the parameter of cubic nonlinearity should be higher than 1. I'd see like that. But at that we need to know what we got as a result of measurements, and in this case we'll be able to assess how large our deformities are, or maybe the cat state is pretty good. Okay, that's clear, thank you. And as for the last remark, indeed the problem to calculate all the probabilities, what's the probability of some other states in the output, is interesting. But as for our problem, as we believe that the cubic phase state is obtained from ideally compressed state, calculating probabilities of obtaining some other states on the output of the scheme is not that interesting, because it will just equal 0, because the density of probability to detect YM is equals 0. But still this problem is interesting, and currently the next another girl, the student of Ivan Vadimovich, is dealing with a problem. Well, let's wish her success. Okay, I'm also satisfied with the answers. Do we have any questions to Natalia? If the members of the board have no. Yes, Nikolai? Well, I have an idea. As an answer to the last discussion, how can we assess the influence of nonlinearity factors to parameter on the quality of cats? It seems to me that in chapter 4 you provide a good criteria, fidelity, because it turns out that if we take the area expansion, we have ideal cats, and all the non-ideal character emerges that we use the function as it is. And what you write about fidelity is really the correlation between ideal cat and the developed cat, obtained cat. And if it's 1, it's okay. And when the system works, the cat is good. If it doesn't, the cat state is bad. I believe you have a pretty good criteria to define it all. And my next comment to the question on probability measurement. And indeed, our cat states, the quality of cat states depend on measurement of probabilities. And I believe you could make it this way. When we design and consider the reduction of the control oscillator, I call it main oscillator. From this, what it actually is, we design our state with P impulse. And if we take square value, it will be a probability. So thus we obtain the probability to get P. We have fidelity for it, and after that we sum it up on the probable values of measurements. And in this case, you'll get an integral fidelity that will meet all the needs during set parameters of the protocol, and it will tell us what optimal options we'll have. So there are two different characteristics, probability of fidelity, and probability is impossible to assess in the scheme due to the model, idealized model, because the parabola has no thickness. Oh, in this regard, okay. So that's, yes, you're based on ideal model here. Yeah, I beg your pardon for the discussion. Do we have anyone willing to ask a question or to comment the work or say something? So please use the microphone. That's Professor Golubov from the Faculty of Physics. Yes, could you please tell me if I got it right? Your system has a good resonator, and inside it has a cavity, an environment, and the field is homogeneous, one mode. Yes? one-mode approximation for the field, and spatial distribution environment inside of the cavity. Is there a contradiction here? Because the environment and the field inside the resonator, they mutually enrich each other. If you used heterogeneous environment, you should have a multimodal field. Can you please comment on that? Igor Mikhailovich, you are talking about the problem considered in Chapter 3. Or do you mean the general consideration? I believe Chapter 3. Yes. Yes, Natalia. There's no need to answer straight away right now, but it's interesting for me to know how you mastered this point. And for you, I believe it would be useful as well. So can I join in? No. No, we don't organize the discussion. Natalia answers. Yes, thank you so much, Yuri Mikhailovich, for the interesting question. Do you hear me all right? No, we hear you well. Well, we presume that atoms interact with one mode of the cavity because other modes are long away, far away from the atomic shift. So that's it that I can answer here. I believe you should think about it in the future. Yeah, sure. Thank you very much for the question. So that is a problem that emerges, and it still goes on and on, though it's clear that the answer should be founded. Yes, I believe I heard this question from you. Yes, I need to think about it. Thank you. No other questions? Do we have any questions submitted via online? No? None? Okay. And we have no external reviews. Therefore, we can shift to the speech of the thesis supervisor. So, please, Ivan, you have the floor. Thank you so much. Yes, I'm satisfied with Natalia's work. She demonstrated a lot of initiative, and you see, the work is pretty good and multidisciplinary. And for the first time, I see that at the defense, the applicant got so many questions from the different fields of quantum optics. And Natalia, I believe, demonstrated that she sorted it out. So she knows some fields well, some fields she knows exceptionally well. And I believe you can assess her literature review as well. These are 3 reviews if you take an ordinary PhD work. So that's incredible work. And based on her discussion, I learned something new, though I'm her thesis supervisor, and it means that she worked a lot. And therefore, I fully believe that this work is successful. Thank you so much, Ivan Vadimovich. I am really pleased to participate in this defense today as well, because I was the supervisor for Natasha when she was a student. And before I shift to the next item in our agenda, I have a question. Now we have an opportunity to switch off the sound of the broadcast. If we need to discuss the work separately, if there are some questions are left that we don't want to discuss publicly, if that's not the case, we can continue. So what are the opinions here? Do we need the closed discussion? No need for that. Okay. Okay, it seems to me that we don't need that. We understand it all and understand the final results. Currently, that's 20 minutes to 4, and we need to shift to the vote, the most important part of our discussion. So I raised the question on the award of the academic degree of candidate of sciences in physics and mathematics to Natalia Masalaeva in specialization 136 optics. And I need to emphasize that voting for the award of the academic degree, each member of the board agrees that Article 11 of the order is not violated by the candidate. And that's the quotation article, quotation of the results of other people. So, let us shift to the vote. Nikolai Nikolaevich, I support this work. Dmitry Vasilievich, I support this work as well. Maria Vladimirovna, yes, I vote for the award of the degree. Igor, I also agree and support this work. I also support this work, and I believe that that's a brilliant work. And everything is okay with it. Well, we unanimously decide. And unanimously voted for the award of the academic degree of candidate of sciences in physics and mathematics to Natalia Masalaeva. So that's our decision. So we made a decision. Natalia, please, you have the floor for the finalizing remarks. Yes, thank you so much. I would like to thank all the members of the board for exceptionally important and useful comments, for some new fields of study, for the discussions, and for private talks with the members of the board. And I would like to particularly thank my thesis supervisor, Ivan Vadimovich Sokolov, who always surprised me, and maybe I managed to surprise him a bit when I managed to catch his form of thinking. And I would like to thank Professor Golubeva for being my thesis supervisor during master courses, and thanks to my lessons with Tatiana Yurievna, I have this basis in quantum optics, and that's, by the way, the achievement of Tatiana Yurievna. And I would like to thank Professor Golubev as well, because when I joined the master course, he read a quantum optic course, and I really liked it a lot, and I thought that it's not by chance that I decided to shift the field of study and switch to quantum optics. And I would like to thank the entire team of quantum optics department that is represented by my friends and colleagues who always helped me, and I hope that we will continue our cooperation. And I would like to thank the Helmut Richard group that I performed part of my thesis there. Helmut himself and his colleagues, and we actively work together, and we continue to work. And I would like to thank my husband, Vyacheslav Kuzmin, who is also a physicist, and he always helps me with his advice. And quite frequently we have discussions on physics issues with him. Thank you so much to everyone. Thank you, Natalia. I forgot to ask the question to the members of the board, and I was reminded that I needed to ask if there are any questions on the procedure of our defense, maybe the ones associated with remote access. Was everything okay? So I need to get everyone's answers. No questions on the procedure. No remarks, no questions. Okay, Dmitry? Yes, everything is okay. Maria? Yes, everything is okay. So, Natalia, we congratulate you with the successful defense and with the award of the academic degree. Okay, thank you so much. So, I therefore close our session, and I would like to thank everyone. Please switch off the